Is this on? So everyone, we're going to get started with our next session. My name is Gina Grassi, and I'll be the session chair for this session. The first paper will be presented by two authors, Ahmed Khalifa and Michael Green, and they'll be presenting general video game rule generation.
Okay, so I'm Ahmed Khalifa, and this is Michael Green, and we're gonna present our paper, which is the general video game rule generation. So why we want to generate rules? Imagine you are a game developer and you are really bored and you don't have any ideas to do. So you can just ask the computer, give me a new idea, and it just produce a prototype, and then you play it and say, oh, it's good, maybe I could develop it in a bigger game. Also, like generating rules in general, in order to make the computer get good rules, you need to understand what's meant by good games. So just researching in this topic will make you understand more about game design and about games. Also, it could be used as an AI challenge, because it's very hard to make the computer get a good game where human can say, yeah, this is a good game, not a shit one. So in order to generate the games, we need some way to describe these games, and we use the video game description language as a language where you can describe different types of games, so the computer can search the space and find new games. And just for simplicity, I just put the key parts of the video game description language, which is the sprite set, which is all the game objects in the game, such as you have an avatar. In this game, you have an avatar, you have spider, you have wall, you have key, and there is a door. Also, there is another section for interaction rules, and these rules are just collision rules. What will happen if two objects collide? For example, if the spider collides with the avatar will die. And the third one is the termination conditions, which says how the game should end. And it's something like if the avatar dies, game lose, or if the avatar reaches the door, you win. And the last thing is the level itself. So there is a way to represent the level as a two-dimensional matrix, and in the end, it will generate a level look like that based on the other information in the VGDL. So we want to make the rule generation, the challenge is a little bit easier, because it's very hard to generate everything, even the level and the sprites and all these objects. So we decided to fix the sprite set and the current level and ask the user to generate only the interaction rules and termination conditions. And still, just to generate interaction rules and termination conditions, it's still a very hard challenge to solve. So our rule generator get from the system all this all the sprite sets and the current level, and it's also to get a forward model where you can simulate your current game, and you have to return back the generated interaction rules and termination condition at the end. So with the framework, we did 3 sample generators with the framework, just to make people understand what's happening. And down there, it's just a generated rule by the first generator, which is the random generator. And the random generator, from the name, it just generates random games. That works. So what it do is just pick 2 different object sprites we have, and then pick a random collision rule, and then says that's a collision rule, and put it there. And for the termination condition, it generates 1 for losing and 1 for winning. The 1 for losing is always fixed. If the avatar dies, you lose the game. While the winning, it could be anything. If timer timed out, the game timed out, or it could just any certain object dies, and that's it. And as you can see, the game down there is broken, because most of the this game, most of the collisions that's there is between objects that never collide, which might be the avatar itself, because he's down the screen, and maybe one of the bases, which is above him, so he never can collide with them. So most of the games by the random is kind of broken. The second one, we tried just to use some knowledge base to improve our games, some ideas and some stuff we know about GVGI itself. And we made the constructive generator, where we designed this template, and we try to fit all different objects in this template and get a game out of it. So what it do, it first categorize different sprite into buckets. There is avatars, there is stuff that you can collect, there is NPCs, there is stuff that move, the boulders there that's moving up and down, they are movable. You have the Diamonds, they are like collectible resource you can collect. And you have the avatar, you have like the door, which is the exit one. After it do that, it put interactions that make sense for each of the category. For example, if you have an NPC is trying to chase the player, he's probably tried to kill him. So by default, there is a high chance this sprite, when it collides with the player, it will kill him. It will never give him a score, like unless it's a suicidal like guy. He's just going there to give you a score and kill himself. So it does this like for all the different categories, and then it generates termination conditions, which kind of similar to the random one. It always lose when the player dies, and you could win if one of the objects that get destroyed in the game from the interaction reach 0. Like, well, as you can see, the player down there can collect the boulders that going up and down and get score out of them. So the winning condition could be if the number of these boulders reach 0, because they can be destroyed. And Mike will continue from here.
So I did the search-based generator. We decided to make this with a FIZPop genetic algorithm. And the reason why we decided to do that is because in the competition, there's a time limit. So in order to more effectively evolve, we decided to split the population into two subpopulations. FIZPop stands for feasible and infeasible. So essentially, one of the populations is infeasible. These games are completely broken. Their goal is to try to get into the feasible population. And the goal of the feasible population is to have the highest fitness in classic evolutionary style. So feasibility was decided using this constraint function, where games that were infeasible had errors that would crash the GVGAI engine. More often than not, they would cause death in the player in the first like 40 frames of the game, which is typically 1 second, and you can't play a game like that. And then this thing that we called bad frames. Bad frames are defined as frames within the game where sprites are drawn outside the boundaries that you can see. Obviously, these games wouldn't be very feasible to play because you wouldn't be able to see what was going on outside the bounds of the game. So we wouldn't really want to play those. And then fitness was decided upon Nielsen's research in relative algorithm performance. So essentially, a really smart agent and a not so smart agent would play the same game, and the smart agent should score better and win more often than the dumb agent would in a good game. Sorry. And then the unique rules, we wanted as many rules in the interaction set to be activated as possible inside of a good game. So that was definitely a factor. And then in game length, we decided that longer games that would be 500 frames or longer, which is about 10 to 12 seconds, would be more interesting than games that would last, maybe like 5 seconds or something like that. So that was considered high fitness. This graph shows similarity of games between all three of the generators. So basically here on the x-axis, we have similarity, which is normalized between 0 and 1, where 0 are games that are very, very similar to each other, almost identical, and 1 would be games that are nothing alike. And then we have it by population density. The similarity is measured by comparing all of the interaction rules inside of a game with all the other interaction rules of all the other games within a same generator's population. So all the random games are compared to all the other random games, and then picking the most similar game to it. And so you see here we have the constructive generator has a very high density, particularly around the 0 and 0.1, 0.1 area. This is because constructive is built on template. So basically you have a template kind of game and you don't really differentiate very far from that. The random has a very particular curve. We're not exactly quite sure why that is, but we have a feeling that it has something to do with the fact that we constrained random to having between 2 and 5 rules. So maybe some of those rules are more similar than others. And then you can see that the genetic kind of makes everything. So it has some games that are very similar to each other, and then it has a few that are all the way over closer to the 1.0, which are games that have nothing to do with anything else, which is, of course, due to the mutation and crossover part of genetic algorithms. We also did a user study. This user study was collected using 161 comparisons. We would give users 2 different games to play, and then they would compare those games and decide either if game A was better than game B, or if game B was better than game A, or if both games were just trash, or if both of them were good. We decided to throw away all the answers that had to do with both of them being bad or both of them being good, because we found that they weren't statistically significant. And then, so that's why you see some of the denominators don't add up to 161. And we hypothesized that the search-based generator should have better games than the constructive, and the constructive generator should have better games than the random. And for the most part, we found this to be true, except for in the aliens game, which was very particular. We had 3 different games for aliens and 3 for their search and for the constructive and the random, and then 3 different games for Boulder Dash and 3 different games for Solar Fox for each generator. And out of the search-based generator alien games, 2 of them had this rule down here, which we highlighted in red. If avatar collides with background, then undo everything, which essentially what that is the avatar is always colliding with the background, and undo everything literally does that. It just goes back to how it was before. So this would freeze the game for the entirety of the game. So users would just see this standstill aliens game that nothing happened. And we hypothesized that happened because the generator thought that would solve its bad frames issue where objects were traveling outside of the frame. So it was like, well, if nothing can move, nothing can go outside the bounds of the frame. And it's not wrong. So that's definitely a fix that we want to try to get in the future, which brings us to our future work, which is to generate better games. Ultimately, the user study showed us that none of the games were particularly fun to play of any of the generators. So there's obviously some work that we need to do there. We want to run the competition, which Ahmed was talking about yesterday. And we want to evolve full games with all 4 of the different parts of interactions, sprites, levels, and stuff like that. So, and that's all that we have. So, time for questions.
Anyone have any questions?
Super short. Okay. Thank you. If you ever find out the way to code fun, how to detect fun in a game, you just give me a call, okay? And if it's possible. And maybe I lost it because I'm sorry, I just entered a few minutes later. What kind of evolutionary system are you using? Are you using grammars for this or something like that? Grammatical evolution or just to play any evolutionary?
No, so what we do is we take the interaction, sorry, can everyone hear me? We take the interaction and the termination sets, and we do simple 1-point crossover and then mutation on top of those. Okay. So it's really, really simple.
And since I've been also using the E5 population, the feasible and feasible population genetic algorithm for other stuff, in our study, we discovered eventually that the number of individuals that were moving from the infeasible population to the feasible population was super low, and that was unexpected. In your case, was like that, or?
I wasn't remember that, but there was like, since the population started at the beginning by using the constructive generator, like the initial population, like 40% is random and 20% from the constructive generator, and there is another 40% mutated version of the constructive. So you can you start at the beginning with some stuff in the feasible population and some stuff that near feasibility. So there is at the beginning I think there was a lot of stuff go to the feasible, but the problem is they go back and forth between them. So.
Yeah, from the feasible to the infeasible, that happens frequently. The problem is
I can't really say that we measured necessarily between infeasible to feasible like all the time, but like what he said, it started off. It started off. There was quite a bit in the feasible population already because of how we initialized the population.
Okay, good. Thank you.
So I like the future work bit about generate games which are actually fun. I mean, where do you think the biggest weakness is in the current system? So, is it to do with the generation, or is it to do with how you evaluate the fitness?
Yeah, it's the fitness.
I would say definitely the fitness. Okay. Yeah, that's definitely.
So one of the things that the bad frames is kind of a little bit sometimes stupid because the system, like let's say our bad frame says if any game have more than 30% of its frames objects are outside, the game is broken. And so you can say if you have the alien games and you have one bullet, but the bullet doesn't have like a collision with the top, and this bullet just go outside of the screen, you will have like 90% of the time like the game is broken. Although all the other stuff is supposed to be working well. So there is like what's called spikes in the fitness, which is not a good thing.
Have you tried running your fitness function on the existing set of GVG AI games?
We didn't do that, but we run it on the constructive generated, like the ones that came from the constructive, and they have high fitness in general. But we didn't try on like the VGDL, like the original ones.
It'd be really worth doing that. And
Yeah,
also,
I think so.
of the current games that are already there, some are actually quite good fun to play, and some are really not. So
Yeah.
things like Camel Race.
Camel Race is not.
Is not.
Wait for breakfast is worse.
Okay. Okay.
You just have to wait doing nothing for like 5 seconds and you win. That's it.
So it'd be really interesting to just run that measure across the entire set of VGDL games that are there already.
Yeah.
And just see if it correlates with how much fun you think they are. Right?
Yeah, I think we need a user study on GVGI games. Yeah.
Yeah, I mean,
All right, everyone go online. No.
but I think having the sort of really large set of statistics for human testing is great. But actually, you can trust your own intuition as well.
Yeah.
So you already know that Wait for Breakfast and Camel Race are really not fun.
Yeah.
And and some of the games are a bit of fun. And just see intuitively, is it kind of making sense?
Yeah, that makes a lot of sense. Thank you.
We do have time for other questions, so please come up.
Yeah, we have a lot of time.
Yeah, we have a lot of time. Short presentation.
First of all, thanks for the this PCG for GVG AI, because it's fun stuff and it's encouraging. My question is, do you have some ideas how to generalize these games without if then elsing everything? Like you said, you have some kind of a constraint goal rules, like always the avatar dies to the lose, and it's kind of like that. So there can be multiple such stats, but we don't have to make the generator like if that then that and so on. So do you have any idea how to
So the search base is supposed to be like that, like there is no if something inside it, it's just supposed to find something that perform well with the agents playing.
But you start with but you mainly start with this rule-based. I mean,
but it's 20%, like, and you have 40% random, so
And
still you have
the rest of the
random stuff.
population is using the search-based generator's mutating function, which is basically just it scrambles everything. So there's a 40%, 20%, 40%.
It either like remove one of the rules or add a new random, totally random one, like with all the permutation it have, or it changes one of the parameters in any of the existing rules to any value that's feasible for it. So.
Yeah.
So simply going more deep into the generating.
That mutation is part of the reason why you see this giant spread on similarity, because some of the games are going to be really, really similar to each other, and part of that's because of the constructive games that already had a pretty good fitness to begin with and kind of stuck with the generator through time, or a lot of their rules did. And then some of the way over there, like near the 0.8, that's because it just mutated into something else that's not related to anything else in the population.
Any other questions? Okay, so let's please thank our speakers for today's presentation. Good job. So I'd like to introduce our next speaker. He looks familiar. He was here in the last session. His paper by Louis Horsley and Diego Perez, entitled "Building an Automatic Sprite Generator with Deep Convolutional Generative Adversarial Networks."
Mouthful. Thank you. Okay, this actually will be short as well. It's a nice story about this paper. Essentially, Louis Horsley is one of the undergrad students at the University of Essex. This is his final third-year project. So this is even before master's level. And the idea is, he said to this project, and we saw, maybe this is quality enough to be sent to somebody that knows about this stuff to get some feedback. There are some people like that here, and apparently it got accepted. So it's kind of a very nice thing. And the idea is well, exactly what it says there. It's trying to build an automatic sprite generator. So I'm basically gonna give the main objectives and the motivation behind why we propose this as a project. And then we're gonna see exactly how has he built the generator, because this is 99% his work. And what kind of sprites have we been able to generate, and some conclusions and future work. So the main objective is to provide some kind of evidence or our first experimentation to see how it's possible to create or to use deep learning of deep convolutional neural networks or with GANs for creating sprite generation. So create new sprites out of some existing sets. The idea is to create sprites that are actually small. So we're talking about 25 by 25 pixels. You might recognize these kind of sprites from the VGDL game, so everything is related. And the idea is to have this system is able to create automatically new sprites out of a set of sprites that we have as input. And I'll explain a bit more about this later, but the idea is to ease the production of sprites, why this would be interesting for small or indie game companies. So in case you have seen or you haven't seen what a generative adversarial network is, or GAN, this is kind of the base of the methodology here. It's a composition of two different neural networks. One of them is the generative one, the other one is the discriminative, the G and the D. And basically there are two networks working against each other. Typically there are two multi-layer perceptrons, and D, or the discriminator, tries to distinguish samples from the model distributions, while the generator tries to create samples that belong or seem to belong to this distribution. In a way, it's like it's typical set that this is a kind of counterfeit against police mode. While you have a set of sprites that belong to the input data that you want, and then you have one of the agents, which is the G, this generator, tries to create from scratch an image that could be part of that set. It wouldn't be strange to be part of the set. And when it tries to create this kind of fake image that doesn't belong to the set, the other one, the discriminator, the police, tries to identify that as one that is not part of the set, the original set. So essentially, that creates a competition between these two networks. One that tries to create a new sample for that follows a model, and the other one tries to identify that one as not part of the set. And the competition between the two is what actually gives these GANs the adversarial part, and it creates some evolution of sprites being generated. So, well, essentially for the sprites, this is the way it works. The good thing about GANs, well, GANs can be used for multiple things, and the idea here is to just take this GAN idea and include it with convolutional neural networks, using the capabilities that convolutions and treating images, as is done in deep learning, and it has been so successful in the last years, include this capability into this methodology of two different networks fighting each other, which gives you the name of deep convolutional generative adversarial networks, or DCGANs. There are some specific, these are described in the paper. There's essentially different things that have been done in the networks by just trying and error, adapting different modifications that can be found in the literature. For instance, using straight convolution instead of max Boolean, trying to modify how the discriminator downsamples the data that it receives, and how the generator has to create sprites or create an image. Tries to help how this upsampling is done. It uses global average pooling. That essentially means that the latest layers are not fully connected. So instead of that, they try to. There are some of the conditions that are not present in order to improve the stability and avoid overfitting, which is one of the problems that Luis found in his study. Another thing that are more normal, like batch normalization, all the input is normalized with a mean 0 and variance of 1. And instead of using ReLUs or rectifier linear units, is using leaky values, which essentially what it does is in the moment when the neuron is not active, instead of giving a value of 0 as an output, gives you a small value, a small negative value. And in general, using these specifics in the networks helped obtaining better results. So if we want to analyze both networks, one of them is the generator. The generator is built with 4 deconvolutional layers. Sorry. The first one is essentially the input, which is an n-dimensional vector. So this is basically, you can see as zeros and ones, basically a random vector. And that goes through 4 different deconvolutional layers. This is the opposite of what's typically seen in image analysis. You have some input, and that input generates an image. So if you just put inside here a random vector of zeros and ones, what you get in the end is basically noise. This has been done with TensorFlow, so I just put this in the slides in case you want to check it. But in general, this is the code that generates these different convolutions or deconvolutions. So this will be the one that tries to generate images. That's why it ends up with an image over here. The discriminator, what it does is the opposite thing. It just takes an image and uses convolutional layers in this case, and tries to end up with, in this case, one value, which is essentially a probability value. And this probability value is this value between 0 and 1, essentially tells you how probable is that this image belongs to one or the other set. So if it belongs to the set that you're trying to discriminate against. Okay. When we put these 2 networks together, the way it works is you have this generator here that basically takes something here and generates an image. And you have a set of training data, and then sample one element from this training data. And both images are thrown through the discriminator. And this comes with 2 different values, P of A and P of V. P of A would be the probability that this new generated image belongs to the set. And this guy is trying to maximize that probability. While P of V is still checking that this one. So, well, let's say the discriminator tries to minimize P of A, so basically find out if this one is not part of the training set, and it still has to maximize the fact that the training data belongs to the training data. Because one thing that the discriminator could do is just saying everything doesn't belong to the training set, and that's definitely something that would work to basically destroy the generator, but you still need to be able to recognize the sprites that are part of the input. So, coming to the experimental work, we essentially have 3 different data sets, and they all of them tackle a specific problem that can be found when trying to work with it. One of them, the first one, is human-like characters. Human-like characters, they are all, I can't remember exactly how many, but there are more than 200, 300 different sprites, and all of them, they look quite similar. They look like, well, you have like a human. You have 2 legs, 2 arms, something that seems like a head. Sometimes you have something in your hands. It's kind of the perfect scenario when you have many sprites that look very nice to each other, and then you want to say, well, let's just create something that could be one image inside that set. Faces. Faces tries to tackle another problem, which is the fact that we have very little samples. In this case, this is a set with only 32 samples. And they are slightly different. They are not as similar as this one, but it's also a first plane of the actual face. So even if they are different, the main problem here is that we don't have many faces. And then the creatures, which is probably it's quite extensive. It's probably even more extensive than human-like characters. We have lots of data here, but they are completely different. We have some kind of a knight, some kind of spaghetti monster, and some kind of a bat or Pac-Man or something. So the idea is we have many different sprites, and they belong to completely different categories. As I said, the training was done with TensorFlow and using also CUDA, and depending on the sets, it was a very fast evolution because we don't have that many data. So if we take a look at the results, essentially for the human-like characters, these are results that actually are very good in general. You have different different evolutions, different iterations for each one of the experiments run, and in some cases you can see how some of the sprites are actually genuinely new. So this is one case where these two are part of the input, and this one is one of the sprites generated. So and you can see some kind of morphing between the two. It's like you take this kind of soldier with this fireman, and then it creates something which is more or less in between. It's not perfect, it has some noise, but it's better than the rest that's coming next. So, yeah. So let's be optimistic about this slide. The next one, faces, it creates something which is not as good. I mean, this is another couple of examples. These are part of the input, and this is part of the output. And this is a problem where, well, essentially what you have is basically a combination of a few different sprites, and then the output is, well, something that looks very similar to that, but with more noise. So very noisy results in this case, but even more noisy is when you have creatures, when you have different kind of blobs. And what you get is essentially small blobs of figures that you can try to identify because you're a human, and you can try, maybe this is a brain, or maybe something different. What we like to say is, well, if the PCG generator cannot create something that you can work with, it can be inspiration for a designer. Well, we want to get better than that. But at the moment, with that variety of sprites, basically what we get is mostly noise. And there are valid reasons for that. So essentially, this, as I said, is a very initial work. Basically, the idea is what happens if we just have all these images, we try to put them through a DC gun and see what we get. And in some cases, these results could be decent and acceptable. But basically, what we are showcasing here is this two different problems: the sparsity of the data, we don't have enough data, and the diversity of the data. But at least for me, this is why this is interesting, because when you have a diversity of data or a sparsity of data, you have a company that cannot afford maybe either buying new sprites or paying somebody that creates sprites for you. You basically can have this system that has the sprite that you have and create new data. Imagine you have you want to create a game out of an army where you have lots of different soldiers, and you want all soldiers to be different, because that's how actually things are. And maybe you have 5 or 6 different soldiers, and from that you can create maybe potentially infinite amount of soldiers with different faces, different colors, different color of the hair, whatever. And that's the actual situation. If you have if that person that wants to create sprites have already 1,000 sprites, well, then it doesn't need to create new sprites. So that's the problem that we're trying to tackle here. And that's why I think this is a relevant problem for somebody to investigate and continue with this future work as well, because it could be a very nice resource for these kind of problems. And then as future work, explore other types of networks, explore other configurations that could be useful. We have used DC guns. There might be a reason not to use DC guns. Could be DC guns bring you the good features of convolutions, but maybe a combination of guns could also work, especially taking into account that the data that we have is very small, so it's possible to use that as well. And of course, this is sprites, but could be applied to some other things. Could be applied to 3-dimensional assets, for instance. You can have I don't know, a collection of vessels, and the vessels are completely created up starting with 5 or 6 different models, and then you have a complete generation of potentially infinite vessels. And then another point that is actually quite important is the need to include novelty. If you have 5 or 6 elements as the input data, the system at the moment what it can do is basically merge what it has, but without including any new things. And there is a lot of research in novelty search or in actually creativity or computational creativity that could also feed into this and add more details or more variation to the sprites that you can generate. And that's actually it.
I'm going to do a similar question to when I did yesterday. Have you thought about incorporating higher level design considerations which enter into the design of sprites? So for instance, there's curves of action, movement, Because a designer, when he designs a character, it's not just thinking about the pixels and convolution the pixels. He's thinking about the certain high-level aspects of the character, the eyes, I don't know.
Yeah, so
the form,
trying to identify different features.
features, high-level features, and he tries then to incorporate in the character. Have you thought about generating like that?
Actually,
From the high-level features?
It's not exactly like that, but we tried, or he tried at the beginning something different, which was trying to say if you are creating soldiers, for instance, then you have weapons, you have a helmet, you have different trousers. So instead of just creating new sprites entirely, just create different parts of them. So let's say you have maybe the weapons, there are 3 or 5 different types of weapons. How can you create new type of weapons? And then somehow match them together and create a new sprite with that. But the problem that we had again was finding the sprites for that. So finding the input data for all these networks, that was the main problem. And with the issue with this particular set, the human-like characters, is that there were enough sprites in that set to be able to generate something. Before that, I don't know, we tried with bicycles as well. And if you look for a bicycle in sprite-like bicycles, in Google you find 1 or 2. So yeah, it's complicated.
Can you go back to the one but last slide? One more till the end. Yeah, this one. It's in the line of the question of Pedro. There are features in the input, like say in the second one you have one color filling the whole sprite. In the first one you have a very clear one color contour.
Yeah.
Would it be possible to extract these features and apply them, 1 or 2 of these features in an output, whatever the form, the shape, the feeling?
I think it would be possible. I don't know if you could get a completely noise-free image, but it could be possible, definitely. Try to identify different parts of the sprites and basically translate
it's
them.
not localized. It's a feature not at a high level, like he said, like this is a weapon, this is a helmet, but it's a graphical feature. There's a clear contour, there's a clear part that is totally filled with one single color, and I really miss this in all the outputs that came out of this. There's a lot of vagueness, a lot of noise, but a lot of
yeah, but it's also, I mean, it's also noise. You see all these dots over here that for some reason are generated.
But the amount of colors in the contour, for example, is astonishing.
Yeah,
it's varying lots of gray and in different colors. This is easier to get.
Yeah, and also easy to post-process. To just take this image and make it smoother as well. Yeah, we're just showing the raw output of the networks. But yeah, that would be possible.
Well, first, I just had a small question, but why did you guys choose a 25 by 25? Because isn't it usually with DC GAN, like you're doubling each size? So I think if you don't stay on like powers of 2, then sometimes the strides don't fit perfectly, and you can get weird artifacts.
I would guess that's basically because that was the data that we had, and I actually went with that.
Okay.
Anything, yeah, probably we didn't even care about that.
And then I wondered, have you seen some of the like the papers where they use GANs on like transforming like a light sketch into an image? I don't know if
yes, sure.
then maybe if creating like little sketches for each of those, maybe that would help with the load data if you just do a transformation instead of creating.
Actually, part of the project was doing a background as well, and creating background in that same way, creating sketches and incorporating texture. But that fell out of the scope of the time that it was. But definitely, it's a good idea. Yeah, it's something we looked at.
So I also want to just add a short comment. From a Spriteset-based view, what those early games often did, because of a memory restriction, they just created one sprite and had different color palettes on it. So for the neural network, it might be interesting to just distinguish between texture and shape. So that you really split this into 2 areas where you have the main sprite and the coloring on top of it. And then you can combine both parts bit by bit.
Yeah, no,
So this might help in producing
it would
another
create
output.
definitely cleaner output at the end. Yeah,
Yeah.
I believe so. Yeah, that's a good idea. Thanks.
Any other questions? Okay, so let's please thank Diego again. And I'd like to invite the next speaker to get ready for their work, please. Which would be? So today we have Alberto Uriati presenting procedural level generation using multi-layer representations with MDMCF.
So hello everybody. As you may notice, I'm not one of the authors of the paper, but they were unable to come here and asked me to present on behalf of them. So I'm going to present the procedural level generation using multi-layer level representation with multidimensional Markov chains. So what is PCG? If you don't know yet what is PCG, I think this is a wrong conference for you. But in any case, it's a creation of content. And if you do this for games, you can create quests like in Skyrim, or items or objects like in Borderlands, or the most typical one, levels, like in Diablo or Spelunky. So there have been a lot of different approaches of like evolutionary algorithms or grammars or fractals. And recently there is some approaches with machine learning based techniques that this requires to have a data set for training them and then sample the content with this trained model. So the motivation of this work is, okay, with the machine learning based approach, they focus on the structural information of the maps. So when you create a level with machine learning, there is no meaning of the places to be there. So there is no design why there are be a pipe there or a block there. You just show up something similar to that with training that data. So is it possible to create the content that takes some focus not only on the structural elements, but in the meaning of the object that you want to place in the levels? So first, I'm going to review the MDCMC approach that, roughly speaking, has three main parts. The first one is you take the level and you make an array of elements. In this case, I have an example of Mario, where each tile you define as an empty or as a ground, or as a pipe, or a block. Then you define a network structure that's gonna represent how the dependencies between the different tiles you want to generate. Here are some, for examples. For example, the NS2, the tile depends on the tile on the left and the tile on the bottom of the tile that you're going to sample. So once you define the network structure, you use all the trained data set to produce the frequencies of these tiles. And then you start to sample a new level. To sample a new level, you can start for some special tiles to define the borders of the map. And you start from the bottom left of the map and keep building all the tiles from row to row until you get the level. From that, you will have a level that looks fine, but maybe it's not playable at all. So you can extend this with some constraint in the sampling. So the idea is to chunk the level in different sections, and in every section you check the constraints if they are validated or not. For instance, you can make an agent that plays the level, and if in a specific section the agent gets stuck, so it's not playable this level, you remove this section and you resample again that section. So now the new contribution of this paper is that, okay, we have the structural layer, but maybe we can add more layer to give some meaning to the things that we are placing in the map. So they propose two different layers besides the structural layer. One is the height layer. So they range from 1 to 5, the different altitudes of the tiles. So now the tiles, they have a knowledge of a place that they're used to be. And the other layer is the player path. So you can define a path that you want to the player follow. So with this, you can add these new layers to the network that we had presented before. And it's like adding more information to the network. So in the blue is the single layer that we had before, and now we have the path layer and the head layer that depends on the tile that you want to sample in this moment. So the idea now is when you want to sample the new map, you are going to have beforehand the different layers. The head layer is always the same, and the path layer you're going to give it beforehand start sampling. So once you're going to start sampling, the tile that you are going to produce depends on the left or the bottom, depends on the network you're using, and the layer of the path and the layer of the height. In this example, we see that the green tile that we want to produce depends on the left and bottom, that are empty tiles, nothing for the path tile, and a 2 for the altitude or the height of the map. They experimented with generating maps for Super Mario. Wow, surprise here. And the experiments, they sampled 1,000 levels using a single layer from the previous approach, and another 1,000 levels using 4 different paths for the player and layer. 2 of them were extracted from one of the training maps, and the other 2 were hand-made. So for the metrics to evaluate the maps produced for this technique, they used the linearity, this is how well the level is approximate with a line, the leniency, that estimates how difficult is the level, and then they added 2 more metrics. One is the Frechet distance, that measures how similar are 2 paths. This is something like you have to think how long should be the row between 2 people following different paths. And the percentage of useful placing springs. So springs is an element that you can jump over and you can jump higher than regular. So usually you can place these objects you need to jump over there to finish the level or not. So that are some experiments and the results. The first one is a single layer that looks okay. And then we have the 4 different paths. The 2 first ones, path 1 and path 2, are extracted from the training data set. So they follow a path from previously maps in the training set. And path 3 and path 4 are handmade for the path. In the path 3, they try to make a plateau area. So towards the end of the level, you can see that the player should be in the top of the level, not all the time the bottom. And for the path 4, they try to add a lot of jumps and really long jumps, and that they produce these kind of maps. So if we see the linearity and the leniency of the maps, these are the heat maps where every pixel is a sample map. And if we compare the standard approach with a single layer and the different 4 maps with different paths, the range of expressive that we can find are pretty much the same. So we are still keeping the structural information of the map that we are able to generate with the first approach. And in this plot is the distance between the different levels. So how likely they are to see that they're similar. Here, the green dots are the trained data set that hopefully you can see that are spread from all the plots. The red dots are using only the single layer. And then the different blues are the different paths. You can see that the path selected to make the path 1 and path 2 are the ones that's pointed. And all the maps generated using these paths are really close to these ones. And then the other 2 paths that are handmade, they are in their own different cluster, but still approaching to some maps that are available in the training set. So if we look at the metrics for the Frechet, we see that the multi-layer with the path, they are really close or it is small. That means that the path that the finally produced the map is closer to the one that we first added to the layer. In the example here, we can see the blue as the path that was barely designed. The red was the path that an AI agent followed with using the A star technique, and the purple is where both agents had the same path at that moment. So the difference is really small, meaning that the intention to produce a jump in the middle of this chunk was achieved with putting some blocks or enemies there. Then the springs, here we can see the average number of springs per map and how the percent of them were needed to complete the map. So in the training data set, 27% of the springs that were there were needed to complete the map, but in the single layer, besides there are a lot of them, like in the training data set, none of them particularly were needed to complete it. While in the multi-layer, their springs were less common, but more needed to complete the level. Here we have two screenshots. The one in the left is the one spring that is not needed to complete the level, and the one in the right needs to be used in order to complete the level. So the conclusion is, with this approach, we are able to introduce some knowledge to or propose to the levels that we want to produce. They want to follow, in this case, a path. And they can learn some mechanisms of the game, like how to use springs that are needed to complete the levels. And the future works, they want to try to use in other domains like Load Runner. They have already experiments that we're going to present in the exec. A way to automatically define other layers and add different layers like difficulty or enemy behavior or aesthetic information. So thanks for listening, and if you have any question, I will try to do my best to answer them, but you have your Sam email address here that he will be more than happy to answer any doubt.
Are there any questions? Our next presenters will be Yu Zhang and Rek Fathomas. They'll be presenting procedural generation of Angry Birds, fun levels using pattern struct and preset model.
Okay. Hello everyone, I am Yu Jiang.
Hi, Rek Fathomas.
Our talk today is procedural generation of Angry Birds fun levels using pattern struct and the preset model.
Okay, before we go into details of this presentation, I would like to mention our overview of our long-term goal for this system. So the concept is like this. From this picture, could you guess what we are trying to do? Okay, see, so we have a module for detecting player emotion, and right bottom, there is also a chatbot system which also considers not only player emotion, but also player activity data, playing log, or even other information. And from these two pieces of information, so the chatbot system will try to come up with some words, okay? that are deemed fit to the current situation of the player. And then those words will be fed to the generator, which will then generate levels. In this case, Angry Birds level, which are formed by suitable quotes or words, like this. So for example, if the player is struggling, so the system is not doing well, he could not kill pigs, so the system will try to show him level like this. Or when, no, don't do that, I do that, I pick this. Okay, when it's time to challenge the player, or maybe it will generate a little bit more challenging level and try to tease the player a little bit with that. Could you read these levels? Okay, cool. Or, for example, if the system detects that the player just arrived in New York, no, that's one, okay. And then, even if it could detect some important seasonal event, yeah, okay. Okay, thank you. So then, my student, he will giving you guys the detail of the system. Okay. In particular, sorry, the work we are presenting today is focused on only this part, the generator part.
Thank you. Okay, first the background. Our research is focused on Angry Birds, a puzzle action video game. In this game, the player uses a slingshot. Uses a slingshot to launch a bird to destroy as many pigs as possible. So the Angry Birds level generation competition has been held at CIG since last year. There are multiple tracks, but we focus on fun track and last year and the difficulty this year. So next, overview and the purpose. Our funny code generator won the fun track last year. This generator can generate code levels and formula levels like this. The purpose of this research I am presenting today is improve our generator based on analysis results of clear, retry, and recognition rates. Here are the complication rules that restrict block types and the number of peaks. Next, I will be introducing some related work. So, examples of generated levels from previous work are shown here. However, all of them didn't consider the fun factor or were not able to generate character patterns. Next, the mechanisms of funny codes. In this game, all objects are affected by gravity and physics. So, except an object named terrain. As a result, care must be taken to generate a character. If not, it will be like this. So in order to implement a stable character, we employed two approaches, the pattern struct and the preset model. In pattern struct, a number of pattern struct files like this prepared for each character. To circumvent the rules on restructure of block types, only one block type will be chosen from usable ones randomly. Then two materials will be randomly chosen, one for forming the character control and the other one for making the character stable. So finally, the terrain will be added under the character. In order to increase the diversity of character patterns, preset model was introduced. This model is used for some letters and numbers like this. So the procedure of generation of a character is like this. This table shows our heuristics for setting the level difficulty. The more number of peaks, the higher difficulty. On the right is the levels. There are levels with easy, normal, and hard difficulty respectively. There is 3 styles were provided to enhance the diversity of single-layered quote levels, as shown like this. Next, the experiments and results. This experiment was conducted to examine the recognition of the words in a level and the clear rate and the retry rate. So participants' information is shown here. Each participant played in random order 5 levels per each difficulty. So the number of peaks and birds setting like this. Before playing, each participant was asked to input all words in the level, display in the level. For each level, 2 retries and 2 retries of inputting and playing were allowed. If they could not input the correct words or clear the level at the last retry, word recognition or level clear is considered failed. Here are the results. First, the word recognition rate is 91.3%, which can be considered successful to play pairs work here. Second, the clear rate and retry rate for each difficulty setting are shown here. These results indicate that most of the created levels can be cleared with 2 retries. However, the difference among the 3 difficulty setting is not clear. This is the example of levels with failed recognition are shown here. This B was generated using its preset model. As a result, we plan to improve the preset model. So these are the examples of levels with failed recognition due to the pattern struct. The letter I was mistaken as the apostrophe in these examples. So here are the comments on Untitled Generator by CIG 2016 reference. We focus on the challenging part and made our decision to also improve it. First, we used this equation to determine which initial peaks will be removed. The peak removed probability distribution for each difficulty setting is shown here. As shown in this distribution, the nearer peaks to the right side, the higher probability will be removed. In particular, for the easy setting, because further peaks are more difficult to shoot, so they are removed with a higher probability. Here are our new heuristics for determine the number of birds according to the number of peaks. In most cases, the number of birds is less than the number of peaks in order to increase the challenging level. So here are the results from the second experiment. First, the clear and the retry rates indicate that levels are more challenging after improvement. Second, the difference among the 3 difficulty setting are also clearer. And the third, distance is most clear in APB. So in addition, difference among the 3 difficult settings in APB are statistically significant. So, however, there are some levels like this. It could not be cleared by participants. As a result, we plan to use AI to check it in advance, whether or not generate levels can be cleared. So here are our conclusions and future works.
So that was our attempt to improve our previous generator last year. And this year, this one of the generators that we submitted this year is called Funny Quotes featuring Dominoes generator. So in addition to quote, we add dominoes, okay? So that you can see that, okay, it has some domino effect once perfectly shot, okay? So we, in this generator, we exploit MCTS to determine location to place objects, characters or dominoes with some fitness function, evaluation function consisting of terms like the number of block types in order to increase the diversity and the number of dominoes being placed, or something like that. Okay, so this, as was announced yesterday, it came second. Okay, but it's first for difficulty metric. By difficulty, it's not mean the most difficult, but it mean in terms of well balanced in difficulty. Okay, so wow, we finished only 5 minutes earlier, okay, than expected. So before I allow you to ask us questions, I would like to invite some of you to play our Angry Birds with our generators, starting with you, Chair. Okay, which one do you want to try, the winner last year or the runner-up this year? The runner-up, oh, okay. Featuring dominoes.
Okay. So everyone has to watch?
Oh, sorry. Maybe you should.
It's a good test then, right? That's actually better if I have it. I'll try it, and if I'm not a good tester, you can get someone else.
Oh, sorry.
Okay.
Maybe we should.
Do I have to?
How come that you cannot see?
Yes.
It's not shown here.
Yes.
Okay.
Oh, you
I
can
can
use
maybe
the
bring it with me. Or?
Okay, okay. Maybe this one.
So what do I do? Push the.
Yes.
What do I do?
You have to use this
slingshot and try to shoot.
like this.
Okay, so just sling it back.
Okay.
Like
Okay.
down, down. Do I press on it?
Do you know where the pigs are? Yes, the green ones are pigs. Okay.
And I want to get them. Oops. You might want to get some. Do I just press down and
Yes.
And drag.
I'm dragging?
Yes.
I'm letting go.
Yeah.
Press down. I'm dragging. See that? And
Yes.
let go.
How about the one on the top?
I know you want me to get that guy, right? That big. Okay. Pressing. See, I'm pressing, but it doesn't.
Press the key.
So see, look, I'm pressing.
Maybe like this. Sorry.
No,
For example, like this one and.
Okay, it is just me. It's not. I suck.
Okay.
Someone else?
Okay.
Someone else like to try. You probably would get someone else, but maybe someone that has played Angry Bird before would want to try. Seems like it's fun. A challenge.
It's not touch, so it should be with a.
Yes.
Maybe we change another level.
Yes.
Okay. So maybe we change to another level. Another
No,
one.
now we start with this. Come on.
Okay. You want to clear this first? Okay, go ahead.
Come on, give me another.
Oh, nice.
It's gonna be. Come on. What's next? Yeah.
Three more.
This is the best. This is a drop. Yeah, but no. You can't double click here, right?
Oh, what's that? What's that?
It's a double click. It's,
No,
it's
not not double click.
right. Oh yeah, here you can do this. All right, let's try further on. Too bad. So guys.
Okay, thank you.
very much.
So I think it's time for questions. Slide dash.
Okay, so I have a question that I wrote down earlier when you were talking about the word recognition when it was it couldn't recognize the apostrophe versus the I. I'm just wondering, I didn't catch why, or do you understand why that happened?
なんかワード認識の結果 experiment one the on about our experiment.
It was trying to create the words. I think it was weave with the apostrophe.
Oh,
or-
yes, yes.
And it put in the I instead. I'm just wondering why?
なん
Or
かその愛を見せエアじゃなくてスライド出してその愛をねアポトフィーに間違えられたやつ。
Maybe this one. This one?
This one? So why? Okay. Okay, so some これ れ何人いたの？
Uh, I,
一人間違えたね。So there is one participant who has mistaken. I don't know. So they are not native speakers. They thought it was I. They probably, yeah, when they input, they input as I. So it's hard to imagine if you are native speakers of English. We did this in Japan. Okay. But probably it's also it's very similar. You see, it looks like the design. It looks like I. So it's also something wrong with the design of this character. It's a design problem. Okay.
Any other questions? Okay, well, I'd like to thank you again. Please, everyone, thank our speakers and for letting us try their demo. That was very great.